welcome to Black and White Week. I hope you've enjoyed the little clips you've seen on our first 3 weeks, from things like Monsters Inc. to Mr. Rogers to last week where we did Cartoon Week with characters like Bullwinkle and Bugs Bunny and Goofy. This week I've decided to focus on some of my favorites from the black and white era. Hope you enjoy them. Oh, and don't forget to learn something about math. You need to do that too. And you can watch me work some of the math problems in this lesson. Oh, and don't forget Scruffy. All right, here's a picture of my beautiful family at Easter, or Easter picture. You can't, it's black and white week, so you can't see the red, beautiful red behind us, but it's red. Our objectives today is mathematical induction infinite geometric series. We're going to find sums of infinite geometric series and use mathematical induction to prove statements. And our vocab is infinite geometric series, converge, limit, diverge, and mathematical induction. Let's start with our first set of problems here. We're determining whether each geometric series converges or diverges. So we're just going to look at the ratios here. And so we'll take our second term divided by our first term, and we'll do the absolute value of that, and if it's less than 1, we know it converges. So we do negative 1/3 divided by 1, which is just negative 1/3. So the absolute value of r is the absolute value of negative 1/3, which is just 1/3. And so since that is less than 1, we know it converges. It will have a sum. And we'll go ahead and do number 3 and 4 as well, like that. So number 3, second term is negative 5, dividing it by 1, so we get negative 5. So the absolute value of r, we're going to do the absolute value of negative 5. And which is that's just going to be 5, but 5 is greater than 1, so this one diverges. It will not have a sum, so diverges. Moving on to number 4 now. Let's do this one at the bottom here. All right, so number 4, second term is 18, dividing it by 27, and we'll need to reduce that down. Let's see, 6 and 9, oh, it keeps going. 2 out of 3, 2/3. So the absolute value of r is equal to the absolute value of 2/3, which is just 2/3. 2/3 is less than 1, so it converges. Not too hard to do, right? We're going to go ahead and look at our next problem set now, and you're going to do those things for 15 through 17. So our next part of our problem set is the sum of an infinite geometric series. We've got a formula for it. And so we're going to do 5, 6, and 7. We're going to find the sum of the infinite geometric series if it exists. So first we have to determine if it exists before we can actually do the sum of it. So number 5, we are taking our second term, 1/2, dividing it by 3/4. And let's see, that comes out to be 2/3. So since that is less than 1, we know it converges. It will have a sum. Now we'll use our formula. So our formula is pretty simple. The formula is just the sum is equal to a sub 1 divided by 1 minus r. So our first term being 3/4, we're going to divide that by 1 minus 2/3, which is going to be 1/3. So that'll be 3/4 divided by 1/3, which is the same thing as 3/4 times 3. And we can show that here using this process. So 3/4 times 3 is equal to 9/4, and that is the sum of our infinite geometric series. All right, let's go to number 6. This time they used a summation notation, so we have to come up with our first and our second terms. So let's go ahead. We'll put, using 4 times 0.25 to the k, we'll take that to the second. That'll be our second term. And then for our first term, we'll just do 4 times 0.25, and that'll be to the first power. And that one's easy. That's just 1/4 of 4, which is 1. The other one, 1/4 squared, 1/16. So 4/16, that's 1/4. So our second divided by our first is 1/4 divided by 1, or 1/4. And that is less than 1, so it does converge. And so we'll use our formula. So S is equal to a sub 1 divided by 1 minus r. And our a sub 1 here, let's see, the first term was a 1. So that'd be 1 being divided by 1 minus 1/4. And it's 1 divided by 3/4, so that's 4/3. So our sum is 4/3 for our infinite geometric series. Number 7. First term, second term divided by first term, it's going to give us 200 divided by 800, and that reduces down to 1/4. So that is our r value, and we know it converges. Using our formula, S is equal to a sub 1 over 1 minus r. Our first term is 800, and we'll divide that by 1 minus 1/4, which is 3/4. So 800 is being divided by 3/4, which is the same thing as 800 times 4/3. Let's see, that doesn't look like it's going to reduce, so we'll do 800 times 4, and that gives us 3,200 divided by 3. Let's put that in mixed number form. That would be 1,066 2/3. So use that process to do the following problems, and you get to watch your first clip here.
There we go again, Junior. We're off on the road to Morocco. This taxi is tough on the spine.
Beats the bus, huh, Junior?
Beats me. Where we're going, why we're going, how can we be sure? I'll lay you 8 to 5 that we meet Dorothy Lamour.
All right, the next thing we're going to do is learn how to change repeating decimals into fractions. And so this is the way we do it. We are going to write it as an infinite geometric series. And by the way, that's Bob Hope and Bing Crosby in the road movies. That's the Road to Morocco. They did a bunch of road movies. They're pretty funny. All right, so our infinite geometric series has 0.888 repeating. So we'll do 0.8 plus 0.08 plus 0.008 plus, and it just keeps repeating that pattern. And they would each fill in, making our infinite geometric series. So our r value would be 0.08 divided by 0.8. And if you work that out, you will get 1/10, or 0.1. So we'll put that down. R is 0.1, and that's less than 1, so it does converge. It does have a sum, which it's got to, because these repeating decimals do have a fraction form. So we'll do a sub 1, which is 0.8, and divide that by 1 minus 0.1, which is going to be 0.9. So 0.8 divided by 0.9. We can just multiply by 10 on both of those. 8/9 is the fraction that is equal to 0.8 repeating. Number 9, we'll do it as an infinite geometric series, and this time it's got 2 repeating digits, so 0.56 plus 0.0056, because we have to fit that in, plus 0.000056, and then dot, dot, dot. And so our r value, we're going to do 0.0056 divided by our first term, 0.56. Well, this time it's not 1/10. This time it's 1/100th, or 0.01. So let's write that down. R is 0.01. So putting in our formula, S is equal to, it does converge because it's less than 1. S is equal to a sub 1 over 1 minus r. So a sub 1 being 0.56. 1 minus r would be 1 minus 0.01. And so that's 0.56 over 0.99. Just multiply top and bottom times 100, you get 56 over 99. And that is the fraction that equals 0.56 repeating. Let's do number 10. Let's see, find some room for that. I think we'll do that on down here at the bottom. So we have, it looks like 1/3 is repeating. So 0.13 plus 0.0013 plus 0.00013 plus dot, dot, dot. Okay, so let's get our r value. That's going to be 0.0013 divided by 0.13. And so that equals, guess what? 0.01, 1/100th. So it does converge. That's less than 1. And so we'll do our formula. S is equal to a sub 1 over 1 minus r. So our first term, being 0.13, is going to be divided by 1 minus 0.01. So that's going to be 0.13 divided by 0.99, which works out to a nice 13/99. So you'll use that process to do these problems here. And we're going to watch another clip. Bob Hope, Green Party.
Off on the road to Morocco. Hang on till the end of the line. I hear this country's where they do the dance of the 7 veils. We tell you more, but we would have the censor on our tails. We certainly do get around. Like Webster's dictionary, we're Morocco bound.
Okay, so the next thing we're going to do is mathematical induction. This is kind of difficult, so just follow the process, and we won't do a whole lot of these. So that was Bing Crosby in the front on the camel, Bob Hope in the back. Bing Crosby famous for White Christmas, Bob Hope famous for entertaining troops. Okay, so let's do our mathematical induction to prove that the sum of the first n even numbers is, and that's the expression. Your first step is to do n equals 1. So we just put 1 in for that n, and we get 2 is equal to n times n plus 1, and we'll put 1 in for n. So 1 times 1 plus 1, and sure enough, that equals 2. So 2 equals 2. Step 2. So the 2, this is where those came from. All right, so step 2, we'll do n equals k. And so we just fill in a k. And we assume that that is true so that we can do step 3. So 2 plus 4 plus 6 plus ... plus 2k is equal to k times k plus 1. Now we're going to add one more term to that. We're going to do step 3, and we're going to do n equal to k plus 1. So one more term. And so n is equal to k plus 1. And what we're going to do is we're going to add the k plus 1 term to the end of the string that we have on that previous step 2. So 2 plus 4 plus 6 plus ... plus 2k plus 1. Actually should have had the 2k in there as well. So that's 2k plus 2 on that side. So it'd be plus 2k plus 2k plus 2. And so it gets those terms. And then that's equal to our k times k plus 1, and then we're going to add one more to that. And so that one is going to be 2k plus 2, because that's what we're adding to both sides, right? So we added a 2k plus 2 to both sides. And so now we're going to simplify that right side and see if we can get it back to looking like our left side. So that's going to give me a k squared plus k plus 2k plus 2. And that's going to give me a k squared plus 3k plus 2. And now we'll factor that. So that's k plus 1 in our first parenthesis. And in our second parenthesis would be k plus 2. Now, a little clever thing here. K plus 1. And look what we do to the second one. We make that a, in a parenthesis within the parenthesis, k plus 1 plus 1. See how we split up the 2? And that, now it matches the other side. And that proves it in a mathematical induction form. So not deduction, but induction. And so we'll go ahead and write that expression out as proven. And we'll have one more type of concept in this lesson. This is probably the toughest one. We won't do a whole lot of these as we do them. And so you'll do problem 24 for that. Now, often counterexamples, you can use negative numbers, 1, 0, or fractions. And so we're looking for counterexamples to disprove these statements. And so we just have to try these numbers out. So we're going to try the different numbers, counterexamples, and we're trying to disprove the statements. We have to stick with real numbers, but we'll use things like fractions, and 0, negative numbers, and you might try different negative numbers, -1. Positive numbers, you might try 1 and then other positive numbers. But your goal is to come up with a number that disproves it. So this first one, n to the fourth is greater than or equal to 1. Let's just try one of them. How about let's try 0. So 0 to the fourth is greater than or equal to 1. And that would just be 0 is greater than or equal to 1. Well, that's not true. And so we just found a counterexample. We have falsified this statement. So we got it on the first shot that time. Let's try 13. So we got the log of n is greater than 0. Now that's log base 10 of n. That's not a base n. So remember how that works? That would be the same thing as saying n is greater than 10 to the 0 power, right? And so n has to be greater than 1. And so what if we chose 0? No, let's try 1. Let's go ahead and do 1. So we'll do the log of 1. And so the log of 1 is greater than 0. And so the log of 1 would be 0. So 0 greater than 0? Well, no, that's false. So it doesn't work. Number 14, we've got this time n to the third less than or equal to 3n squared. And let's see, what kind of number shall we choose this time? Maybe we'll choose a value of n. Let's try a negative number. Let's do -2. And so that I do -2 to the third. And remember, negative bases have to be in parentheses. Is less than or equal to 3 times -2 to the second. So that's -8 is less than or equal to, let's see, that'd be 4 times 3 is 12. And well, that's a true statement. Oh, well, we haven't found a counterexample yet. Well, maybe we could try a positive number this time. Let's try 5. So let's go 5 to the third, less than or equal to 3 times 5 to the second. And so 5 to the third is 125, and that would be less than or equal to, well, that'd be 25 times 3, 75. Well, that's not true. So we have found a counterexample and made it false. All right, you're going to use that for these. We're going to watch our final clip. Hope you've enjoyed this, and you have a great day.
We're off on the road to Morocco. Look out!
Well, clear the way,
Yes, here we come. The men eat fire, sleep on nails, and saw their wives in half. It seems to me there should be easier ways to get a laugh. We're off on the road to Morocco, and somewhere I feel kind of numb. For any villains we may meet, we haven't any fear. Paramount will protect us 'cause we're signed for 5 more years. We certainly do get around like a complete set of Shakespeare that you buy at the corner drugstore for $1.98. We're Morocco bound. Or like a volume of Omar Khayyam that you buy at a department store at Christmas time for your cousin Julia. We're Morocco bound.
No more classes, no.
Say goodbye to Scruffy, and you guys have a great day. We'll see you tomorrow.